Hey guys, welcome back. This time around we're going to look at two key concepts associated with neurophysiology, those being resting membrane potential and the polarized state. At rest, there's no electrical events being conducted down the neuron. Now that makes sense because if there's electrical events going down the neuron, it's going to stimulate a muscle contraction too. Now when there's no electrical events going down the surface of the neuron, the axonema, or the sarcolemma of the muscle, we say that those lemmas are at resting state. At resting state, they do have the potential and the ability to do work. And that is because they have channel gates and ion concentration differences. But to do work, we've got to open up those gates and allow those ions to move across them. So at rest, those gates are closed, no ions moving basically. So we can say that that lemma is primed and ready to go, as you can see from this image. At that moment, we can say that the cell is at resting membrane potential, or what's known as RMF. At resting membrane potential, the cell does have the possibility to do work because it has net charges on either side of the membrane. Let's think about that just a minute. Here you see again a voltmeter measuring both sides of this given membrane. And you do have a polar state there if you want to think about it. You have a positive pole on the outside and a negative on the inside, much like a battery has opposite poles. Now, if a battery has a net voltage to it, then we say that that battery is charged. In a human body, if we have a net charge across that plasma membrane, we say that that plasma membrane is polarized. It specifically means in this case that the cytoplasmic side of the neuron cell's axonema is electronegative in respect to the electropositive charge found outside that axonema in the extracellular space. Now it's important to back up just a moment and say that there is a net charge over that very limited area associated with the plasma membrane. That net charge is not going to be found if we were looking inside the cell as a whole, because inside the cell as a whole it's going to be net neutral. Our body's net neutral. But there are those limited spaces in which we do have net charges. Now again, this potential is called the resting membrane potential, and we can say that the axonema and or the sarcolemma is polarized at rest. With the key cations that we can see associated with the lemmas being sodium and potassium. Notice from this image that there's a very high concentration of sodium on the outside of the cell and a very low concentration in respects on the inside of the cell. Notice the flip side on the potassium. There's a high concentration of potassium on the inside and a lower concentration on the outside. Now let's just think here a moment. If I had a channel or a protein pore created there that would allow sodium to move, which way would sodium move? I hope you tell me that sodium would move from the outside to the in using simple diffusion. The flip side for potassium, if potassium could move across that plasma membrane, it would move from the inside out. Other ions that you can see here are chlorine. There's a very high concentration of chlorine on the outside, a very low concentration of chlorine on the inside. And then there's that A negative player over there. That A negative is an anionic protein that is non-permeable, period. And it's only going to be found in the cytoplasmic side. Now, if you ignore that anionic protein for a moment and start looking at the potassium and sodium and chlorine ions, really, if you just look at them as they look here on this depiction, the outside is actually more negative than the inside. So it is these anionic proteins that tip the table and make the inside more negative. They're a key player, but they're not the only player. The things that make the resting state what it is going to be the differences in the concentration of the ions that you see here, the sodiums, the potassiums, and the chlorines. It's also going to be the difference associated with that anionic protein. But there's two other players that are going on here as well. The first one's going to be a pump mechanism. Notice from this image here that there is an active pump that can be found associated with the plasma membranes that will be at work during resting state. Now this is going to be an ATP-driven sodium-potassium pump. Now notice with this sodium-potassium pump, for every 3 sodiums that are pumped out into the extracellular fluid, 2 potassiums will be pumped back in. So the net gain is each time this pump works, a net positive charged ion is going to be moved out, making the outside more positive than the inside. And then the other very, very essential component here is to take a look at the permeability coefficients of the ions that we're talking about here. At rest, the cell membrane is totally impermeable to the large anionic proteins. So they're going to stay inside that cell, making inside negative. Now that sodium is slightly permeable at rest. That means it's slightly leaky. So sodium will move in and bring with it its positive charge. But potassium is about 75 times more leaky than sodium is, and potassium will move out. So for every sodium that moves in, you'll have 75 potassiums moving out, making the outside more positive at rest and ensuring that that ATP pump has to work continuously. And finally, those chlorine ions are going to move freely at rest. And remember, you've got about 120 millimolar concentration on the outside, only 10 on the inside. So they're going to move inward at rest, bringing with them their negative charge. So the fact that we have concentration differences, the fact that we have the impermeable anionic protein, the fact that we are pumping more sodium out than we bring potassium back in, and the fact that we have potassium and chlorine much more leaky than sodium is, results ultimately in a resting state in which the outside surface is going to be positive in respect to the inside surface. Membrane potential, especially in neurons and muscles, acts as the communication signals for receiving and integrating and sending information. The things that can change the membrane potential at rest are going to be things such as anything that changes the membrane permeability to any type of ion, and anything that alters ion concentrations on the two sides of the membranes.